When night falls, the sky darkens, and the ground grows quiet. A silent dialogue begins between Earth and the star that has sustained us for billions of years, the Sunday. This conversation uses no words. There is no sound, no obvious motion. Instead, it appears as curtains of light folding like rivers of silk, rolling like waves, and breaking into drifting fragments of color that spread slowly across the northern and southern skies. That is Aurora, the northern and southern lights, a phenomenon that is both breathtakingly beautiful and rigorously precise, poetic to the eye, yet rooted completely in physics. It is a light symphony written by plasma, magnetic fields, electric charges, and the upper atmosphere, and received by humans as emotion, awe, humility, and respect for the scale of the universe. When you look up and see bands of green, violet, and red flowing across the sky, you're not just witnessing something pretty. You are watching your own planet respond to a signal from the Sunday. You are seeing electrons that have traveled 150 million kilometers to meet Earth in the final moments of their journey. You are seeing the magnetic field, the planet's invisible armor, drawing those particles in and turning that interaction into the most spectacular horizon nature can paint. And as those bands brighten, twist, and then fade, you are effectively watching the pulse of the magnetosphere, the flow of interplanetary plasma, magnetic reconnection events more powerful than lightning, and the traces of eruptions that could disrupt modern civilization if they repeated today. Aurora is not just beauty. Aurora is a window into the solar system, a live map of energy interactions, a slow-motion recording of how a planet both protects itself from and interacts with its star. Today, we'll explore the science of auroras, not as a dense lecture, but in a calmer, more readable rhythm that still lets your mind stay relaxed. Let's walk through 10 chapters, each a slice of space physics from the birth of electrons on the Sun to the moment they strike oxygen in Earth's upper atmosphere and become the soft green light nature is so well known for. Release the tension in your shoulders and let Aurora open in front of you, like a story written in plasma and light. Chapter 1, Aurora, a meeting between the Sun and the Earth. To understand auroras, we have to start far away at the surface of the Sun, where temperatures reach over 5,500 degrees Celsius, and tangled magnetic field lines are constantly rising, sinking, twisting, and reconnecting. The Sun is not a quiet, static ball of fire. It is an ocean of plasma where magnetic structures rise like loops, shear, and sometimes snap, producing explosive events, solar flares, and coronal mass ejections, CMEs. During these eruptions, the Sun releases billions of tons of charged particles, mainly protons and electrons, into space at speeds of up to millions of kilometers per hour. This outflow is the solar wind. Most of the time, the solar wind is relatively gentle, like a warm breeze spreading through the solar system. But at times, it becomes a full-scale storm. When that storm reaches Earth, auroras begin. Imagine Earth as a sphere surrounded by an invisible bubble. This is the magnetosphere. It's a magnetic shield that deflects most of the high-energy particles from the Sunday. When a strong solar wind hits, most particles slide around this shield, like water glancing off armor. But some become trapped, guided along magnetic field lines toward the weakest regions of the magnetosphere, the magnetic poles in the north and south. That is where auroras start. High-speed electrons plunge into the atmosphere along these field lines, moving at thousands of kilometers per second. When they collide with oxygen and nitrogen molecules at altitudes from roughly 100 to over 300 kilometers, they transfer energy to those atmospheric particles. The excited atoms and molecules then relax back to lower energy states and emit light. That light is aurora. No magic is required. No mystery is required. Just physics in one of its most beautiful forms. The remarkable part is this: the journey from Sun to Earth spans 150 million km, yet it ends as thin, delicate curtains of light in our night sky. Each arc of light is essentially a visible afterglow of a solar eruption that occurred days earlier at the Sunday. When electrons hit oxygen at higher altitudes, above to 200 kilometers, they generate red light. At lower altitudes, about 150 kilometers, the same oxygen produces green, the most common auroral color. Nitrogen contributes blues and purples and, in some conditions, pinkish tones where colors blend. The entire sky becomes a giant natural laboratory where each atom behaves like a tiny emitter, adding its own spectral line to a cosmic light show. The most subtle aspect of aurora is not the color, but what it means. Auroras are a direct, visible indicator that the sun is interacting with Earth. An electron launched from a small eruption on the sun may take nearly 2 days to arrive here. It carries information about conditions in the solar corona, magnetic structure, plasma energy, and properties of the solar wind. At the moment it strikes oxygen or nitrogen in our atmosphere, it tells that story as light. In that sense, aurora is not just beautiful, it is a form of memory, a luminous record suspended between the solar wind and Earth's atmosphere. Auroras also reveal the health of the Sun-Earth connection. When they are bright, fast, and extend to lower latitudes than usual, it signals a period of stronger solar activity and more intense coupling with Earth's magnetosphere. When they are faint and confined to high latitudes, the system is relatively calm. In the next chapter, we'll look more closely at the language of color, how each atmospheric constituent produces its own shade, like a spectroscopic code written across the sky. Chapter 2: The Language of Light, when elements speak in the sky. Auroras are not just an aesthetic display. If you look long enough, each band of light reveals a deeper layer of physics, the language of atomic transitions, of electrons changing energy levels, and of the atmospheric composition of our planet. It is no coincidence that auroras appear green, pink, violet, or deep red. Each color is a scientific fingerprint, a unique signature of a specific atom or molecule being energized by incoming electrons from space. When high-speed electrons from the solar wind enter Earth's upper atmosphere, they collide with oxygen and nitrogen, the two primary components of the air we breathe. These collisions transfer energy, pushing electrons in those atoms and molecules into higher energy states. When they fall back down to their original levels, they release photons. That is the core mechanism of auroras. Billions of quantum jumps per second, scaled up into vast curtains of light stretching thousands of kilometers. What makes auroras truly fascinating is that each element emits different colors. The night sky becomes a natural, planet-sized spectroscopy experiment where you can literally see quantum mechanics with your own eyes. Oxygen, the source of green and red. Oxygen is a familiar element on Earth, but at altitudes above to 100 kilometers, it becomes the main artist of auroral colors. At to 150 kilometers, In the rarefied upper atmosphere where collisions are relatively infrequent, atomic oxygen emits green light at a wavelength near 557.7 nanometers. This is the bright green commonly associated with auroras, smooth, widespread, and curtain-like. At higher altitudes, around 200-300 kilometers, oxygen can emit red light at about 630 nanometers. This red emission is weaker and less common, typically appearing during strong geomagnetic storms when energy input is high. The red line of oxygen has a special constraint. The excited state responsible for this emission is long-lived and will be quenched if the atom collides again before it radiates. At lower altitudes, where the air is denser, frequent collisions suppress red emission. Only in thin, higher layers, where collisions are rare, is the red glow allowed to appear. So whenever you see a red auroral glow, you're observing processes occurring far above your head, in a region where the atmosphere is almost gone and isolated oxygen atoms are quietly radiating in the dark. Nitrogen, the source of violets and blues. If oxygen paints the greens and reds, nitrogen supplies the blues and purples. Nitrogen is present both as atomic N and molecular N2. When these are ionized or excited by energetic electrons, they emit at shorter wavelengths that appear blue or violet. These colors often outline the lower edges of auroral curtains, where electrons penetrate deeper and have higher energies. Because human eyes are less sensitive to violet and deep blue in low light, these hues can appear ghostly or indistinct, almost otherworldly. Sometimes, nitrogen and oxygen emissions overlap in space and time, creating smooth gradients of color. Green fading into violet, red blending into pink. The result is not a simple striped pattern, but a continuously evolving tapestry of mixed spectral lines. Altitude controls the palette. Auroras depend not only on which element is emitting, but also on altitude. Above to 250 kilometers, red oxygen dominates. 100-150 kilometers, green oxygen is strongest. Below to 100 kilometers, nitrogen-driven blues and violets appear. Looking at a well-developed aurora is like looking through a vertical cross-section of Earth's atmosphere, encoded in color. Long exposure images often reveal a three-layer structure: red at the top, green in the middle, and blue-violet near the bottom. Each layer corresponds to different densities, energies, and dominant emission processes, all happening simultaneously. Energy controls the shade. Electron energy also shapes the aurora's appearance. Lower energy electrons more easily excite the states responsible for green oxygen emission. Higher energy electrons can penetrate deeper and preferentially excite nitrogen, enhancing violet and blue light. Extremely energetic events can drive strong red emission at high altitudes. This means that the aurora's color balance is a direct indicator of geomagnetic storm intensity and the energy distribution of incoming particles. Scientists can read auroral colors to infer how much energy the sun has injected into near-Earth space. You can think of aurora as a giant piece of music. Energy equals volume, element equals instrument, atmosphere equals concert hall. When the solar storm is strong, the music is loud and intense, with complex colors. When the solar wind is gentle, the aurora is soft and predominantly green. Auroral light, quantum mechanics written in color. Behind every auroral photon is a single electron changing its energy state. Quantum physics is unfolding silently above you, at atomic scales. Yet when trillions of these emissions occur together, they create structures big enough to fill the entire horizon. When you watch the aurora, you are seeing the interplay between the microscopic world of electron transitions and the macroscopic world of an entire planetary atmosphere, two scales that rarely meet in human experience, united in one phenomenon. Chapter 3: Aurora as a living map of Earth's magnetic field. If you see aurora for the first time, you might think it's a random glow, as if the atmosphere simply decided to light up in moving patterns. But the longer you look, the more obvious it becomes that something organized is shaping the light. That something is Earth's magnetic field, a powerful, invisible structure operating continuously over billions of years. Aurora is not just light. It is a live map drawn by electrons and protons from the Sun, guided by Earth's magnetism. Every curve, fold, and crown of light traces the geometry of magnetic field lines in near-Earth space. To understand why auroras form as long curtains, fast waves, or overhead crowns, we have to examine the invisible skeleton controlling them, the magnetosphere. Curtains of light, traces of magnetic field lines. One of the most common auroral forms is the thin, elongated curtain sheets of greenish light, drooping like fabric and extending hundreds or thousands of kilometers. These appear because electrons are constrained to travel along magnetic field lines that loop from one polar region to the other. Think of magnetic field lines as invisible wires. Electrons do not simply fall straight in. They spiral and slide along these wires, entering the atmosphere where the field lines intersect Earth's upper air. Because field lines converge and intensify near the poles, auroras are strongly concentrated in those regions. As electrons stream down along the field lines and collide with atmospheric particles, the emission zones line up into bands parallel to the local magnetic geometry. That's why the aurora seems to self-organize into stripes and curtains instead of a uniform glow. Traveling waves, signatures of space-borne electric currents. Sometimes auroras seem to race across the sky, as if a wave of brightness is moving along their length. This motion is linked to large-scale current systems called Birkeland currents, enormous electric currents flowing along magnetic field lines between space and the polar atmosphere, first proposed by physicist Christian Birkeland. These currents can reach to 1 million amperes or more. When Birkeland currents fluctuate, they modulate the precipitation of electrons and thus drive moving auroral forms, wave-like brightenings that sweep across the sky. In those moments, you are literally watching electrical currents in near-Earth space, mapped directly into visible light. Auroral crown where magnetic field lines converge overhead. One of the most dramatic auroral forms is the corona or auroral crown. When the light seems to explode from a point overhead and radiate outward like spokes in a halo. This occurs when you stand under a region where field lines are nearly vertical and strongly converging. Electrons are then funneled downward almost directly above you. Visually, all the auroral rays appear to converge, giving the impression of a luminous dome or gateway opening in the sky. Scientifically, you are seeing the direction of electron precipitation, the strength and orientation of the local magnetic field, and a three-dimensional cross-section of the magnetosphere geometry above your location. The auroral corona is effectively a direct projection of field line geometry onto your sky. Auroral oval, the fixed, large-scale structure, Auroras cluster in an annular region around each magnetic pole called the auroral oval. This ring is not rigid but expands, contracts, and shifts with changing solar wind conditions. When the solar wind is strong, the oval widens and moves equatorward. Auroras become visible at lower latitudes, and plasma activity intensifies. This behavior reflects changes in the magnetosphere: compression on the day side, stretching of the night side tail, and enhanced energy input. By monitoring the auroral oval, scientists can assess the state of Earth's magnetic environment in near real time. Auroral light as a dynamic plasma map. If the magnetic field is the skeleton, plasma is the blood. Auroral structures reveal where that plasma is flowing and how it is being energized. Bright regions, high particle precipitation, flickering or pulsating structures, unstable currents and waves. Rapid color changes, varying energies and densities of electrons. Horizontal wave motions, oscillating Birkeland currents. Sudden brightenings and breakups, magnetic reconnection events in the magnetotail. High-speed imaging of auroras allows scientists to reconstruct the underlying plasma processes, something that would otherwise require a fleet of spacecraft. Auroras are therefore not just visually impressive, they are a natural diagnostic tool for geospace physics. Aurora helps us see the invisible. Without auroras, we'd rely exclusively on high-altitude satellites, plasma detectors, spaceborne magnetometers, ionospheric radars, and in situ particle instruments to infer the structure and dynamics of the magnetosphere. With auroras, we gain a direct visual overlay of all these processes. The night sky itself becomes a diagnostic display, showing where the field is strong or weak, where currents are flowing, where plasma is precipitating, and where the solar wind is strongly coupling to Earth. In that sense, Aurora is light but also a dynamic map of a planetary scale electromagnetic system. Chapter 4. It all starts in Earth's magnetic tail. If the aurora is the visible dance, its deep energy source lies in a vast, dark structure far larger than any continent, Earth's magnetotail. This is the elongated night-side extension of the magnetosphere, stretching millions of kilometers away from the Sunday here. Earth's magnetic field is pulled into a long, feather-like tail by the solar wind. In this region, subtle plasma processes can release enough energy to light up thousands of kilometers of sky. Long before auroral light appears, a chain of hidden events takes place in the magnetotail. Plasma flows, field lines stretching, and most crucially, magnetic reconnection, one of the most powerful energy conversion mechanisms in astrophysical plasmas. 1. The magnetosphere, a distorted, comet-like shield. Earth's intrinsic magnetic field resembles that of a dipole, but the solar wind distorts it dramatically. On the day side, facing the sun, the magnetosphere is compressed to around 10 Earth radii. On the night side, it is stretched into a magnetotail that can extend hundreds of thousands to over 1 million kilometers. This region is critical for auroras because it stores and releases much of the energy that eventually drives substorms. Think of it as a reservoir. The solar wind continuously injects plasma and magnetic flux, stretching field lines like taut rubber bands in the tail. 2. Magnetic reconnection, the trigger. In the magnetotail, field lines can be stretched so far that they break and reconnect in new configurations. This process, Magnetic reconnection is ubiquitous in astrophysical plasmas from the Sun's corona to distant nebulae. When reconnection occurs in the tail, magnetic field lines snap and rejoin. Stored magnetic energy is rapidly converted into kinetic and thermal energy. Particles are accelerated in opposite directions. One beam of energized plasma is ejected down the tail, away from Earth. The other is directed earthward. This earthbound population of energetic electrons is what ultimately powers auroras. 3. Substorms controlled explosions in near-Earth space. When enough magnetic flux and plasma energy have built up in the tail, reconnection triggers a localized energy release called a substorm. A substorm evolves in 3 main phases. Growth phase. The solar wind steadily pumps energy into the magnetotail. Field lines stretch and the tail becomes more elongated. Expansion phase. Reconnection sets in. Magnetic energy is released over tens of seconds to minutes. Electrons are accelerated and precipitate into the polar ionosphere, brightening the aurora. Recovery phase. The system relaxes toward a lower energy state. Auroras fade and the magnetotail gradually returns to a less stressed configuration. A single substorm can illuminate the high-latitude sky for an hour or more, yet the engine is a compact reconnection region, hundreds of thousands of kilometers away. 4. Plasma flows toward Earth, the last step before light. Once accelerated, electrons stream along magnetic field lines toward Earth's poles. Along the way, they interact with plasma waves and smaller-scale magnetic structures, gaining or losing energy. They do not fall straight down. Instead, they spiral along the field, moving at thousands of kilometers per second. When they finally collide with oxygen and nitrogen at altitudes of 8,300 kilometers, auroral emissions are produced. That is the final step. Magnetotail physics converted into visible light. 5. Why the magnetotail controls auroral structure. Auroral morphology: curtains, arcs, rayed structures, crowns, reflects the magnetotail's state. Strongly stretched tail, thin, well-defined arcs. Intense reconnection, sudden auroral brightenings and breakup. Weak solar wind, faint, relatively static auroras. Strong solar wind with southward IMF, expanded auroral oval at lower latitudes. Unusual events, such as auroras, visible in mid-latitude regions, for example, over southern Europe or East Asia, are often linked to extreme disturbances in the magnetotail during powerful geomagnetic storms. 6. Magnetotail as a natural plasma laboratory. The magnetotail is where scientists directly study Alphen waves transporting energy along field lines, electron acceleration comparable to that in particle accelerators, magnetic reconnection relevant to nuclear fusion devices. By measuring these processes in situ with satellites, we improve our understanding of energy transport in plasmas, knowledge essential for advancing controlled fusion as a potential clean energy source. 7. Auroras as messages from the magnetotail. When auroras brighten overhead, they carry encoded information about solar wind speed and density, the orientation of the interplanetary magnetic field, the stress state of the magnetotail, and the magnitude of recent reconnection events. Auroras are the visible endpoint of a long chain of plasma interactions between Sun and Earth light as the final status report of a planetary scale energy system. Chapter 5: Aurora as a global and cosmic phenomenon. For a long time, Aurora auroras were thought of as a special feature of Earth. But as space exploration expanded, we learned that auroras are not exclusive to our planet. They are a universal phenomenon. They appear wherever a star's plasma wind interacts with a sufficiently strong magnetic field and atmosphere. That is why, physically speaking, auroras are a kind of universal language of magnetized planets and even some failed stars. At the heart of every aurora, whether on Earth, Jupiter, or a distant brown dwarf, lies the same basic mechanism: a flowing plasma, stellar wind or internal plasma source, a magnetic field, and a medium where particles can precipitate and emit light or radio waves. In our solar system, Jupiter is the master of auroras. Its magnetic field is about 20,000 times stronger than Earth's, and its magnetosphere is so large it engulfs several of its moons. Volcanically active Io ejects sulfur and oxygen into space. Jupiter's magnetic field captures these ions and channels them into its polar regions, creating auroras so powerful that they radiate intensely in ultraviolet and even radio wavelengths. These magnetic footprints of moons like Io, Europa, and Ganymede can be traced within Jupiter's auroral patterns. Saturn also hosts auroras, softer than Jupiter's but still much stronger than Earth's. Cassini's observations revealed auroral rings at Saturn's poles, driven by both solar wind and internal magnetospheric processes. Because Saturn's upper atmosphere is rich in hydrogen, much of its auroral emission lies in ultraviolet, invisible to the naked eye, but spectacular in instrument images. Uranus and Neptune, the ice giants, have highly tilted and offset magnetic fields. Their auroras are irregular and harder to predict, reflecting these complex internal field geometries. Yet they still follow the basic rule: plasma plus magnetism equals aurora. Perhaps most strikingly, brown dwarfs, failed stars that never sustained full hydrogen fusion, also exhibit aurora-like emissions. Some of these auroras are detected not in visible light, but in radio wavelengths. In 2015, astronomers observed auroral radio signatures from a brown dwarf to 20 light-years away. Here, the plasma and magnetic interactions seem to be self-generated rather than driven by an external stellar wind, suggesting that auroral physics can operate purely with internal dynamos and magnetospheric processes. This broadens our view. Auroras are not just planetary phenomena. They are manifestations of plasma and magnetic fields wherever sufficient conditions for particle acceleration and precipitation exist. What does aurora tell us about the universe? It reveals magnetic fields. Magnetic fields are a fundamental agent shaping plasmas across the cosmos. Wherever we detect auroral emissions, we know there is a structured magnetic environment. It hints at habitability. A strong planetary magnetic field helps shield atmospheres from being stripped by stellar winds, preserving water and enabling long-term climate stability. Detecting auroral signals on exoplanets may thus indirectly indicate the presence of protective magnetospheres, one ingredient in the broader question of habitability. It shows that stars and planets are in constant dialogue. Traces of aurora are signs that a world is electromagnetically connected to its star or local environment. Each burst of light and radio emission documents energy exchange. Auroras, then, are not just visual spectacles. They are signatures of connection, evidence that worlds across the universe continuously interact with their surroundings. Chapter 6: When Aurora Touches the Atmosphere. Subtle effects on Earth. High above Earth's surface, in regions where air is too thin to carry ordinary sound, auroras subtly modify our planet, not with dramatic storms or eruptions, but with small, precise changes in chemistry, temperature, and atmospheric dynamics, some of which propagate downward over time. Earth is not a closed system. It exchanges energy with space, and auroras are one of the clearest interfaces where that exchange happens. 1. Electron impacts and atmospheric chemistry. Between roughly 90 and 300 kilometers altitude, incoming energetic electrons collide with atmospheric constituents, O2 and O, oxygen, N2 and N, nitrogen, and trace species like H and He at higher levels. These collisions do more than produce light. They also drive chemical reactions, including the formation of nitric oxide, O, a molecule that influences ozone chemistry. While ozone resides primarily at lower altitudes, changes in NO at high altitudes can eventually affect ozone balance in the middle and upper atmosphere, especially over polar regions and during periods of strong geomagnetic activity. This is analogous to dropping a pebble in a pond. The disturbance starts in one layer but sends ripples outward and downward. 2. Heating and thermospheric expansion. Auroral precipitation deposits energy as optical emissions, local heating of gases, enhanced particle motion. The upper atmosphere, particularly the thermosphere, can warm and expand in response. This expansion increases atmospheric density at satellite altitudes. Even a small density increase translates into higher drag on satellites and debris, leading to orbital decay, shortened satellite lifetimes, and altered collision probabilities in low Earth orbit. Thus, auroral activity directly couples space weather to satellite operations. 3. Links to climate, slow, indirect, but real. Auroras are often referred to as a space weather chart. They visualize energy input from the sun into the geospace environment. Solar activity follows an 11-year cycle. At activity peaks, increased auroral activity correlates with shifts in upper atmospheric temperature distributions, ozone concentrations in polar regions, circulation patterns in the mesosphere and stratosphere. Auroras themselves do not cause surface weather in a simple one-to-one way, but they participate in a complex chain of processes connecting solar variability to Earth's climate system. They are visible traces of that coupling. 4. Impacts on technology, signals and systems. Auroral events influence GPS accuracy, high-frequency radio communications, aviation and maritime navigation, long-distance radio links. Particle precipitation and associated currents modify the ionosphere's electron density structure. This alters how radio waves propagate, bending, scattering, or attenuating signals. A short auroral burst in polar regions can temporarily disrupt communication and navigation over large areas, even though the disturbance is invisible to people on the ground. Auroras thus serve as natural tests of the resilience of our technological infrastructure to space weather. 5. Global electric circuits and currents. Auroral regions are part of a larger planetary-scale electrical system. When the solar wind interacts with Earth's magnetosphere, it drives field-aligned Birkeland currents, ionospheric currents, global electric potential differences. These currents couple space plasmas to the conducting atmosphere and, indirectly, to the solid Earth. They can induce geomagnetically induced currents, GICs in power grids, pipelines, and other large conductors. Auroral brightness often correlates with the intensity of these current systems. 6. Auroras and ozone. Strong auroral activity can enhance NO and other reactive nitrogen species in the upper atmosphere. These can participate in catalytic cycles that deplete ozone in certain layers. While these effects are localized and much smaller than human-driven ozone depletion, they form part of the natural variability of the ozone layer, especially in polar regions and during polar night. Understanding this top-down influence helps refine climate and atmospheric models. 7. The visible edge of invisible processes. In space physics, a common phrase is, Aurora is the visible edge of invisible processes. Beneath the light you see are plasma instabilities, electromagnetic waves, energetic particle populations, and coupled chemical and dynamical changes in the atmosphere. Aurora is the part we can see, the signature that reveals internal workings that would otherwise remain hidden. Chapter 7. Invisible waves in Earth's breath. Auroral energy input does more than create light and chemistry. It also perturbs the way the atmosphere itself moves and breathes. Electron precipitation and Joule heating in the high-latitude upper atmosphere generate gravity waves, atmospheric tides, and large-scale circulation changes. Nitric oxide, NO, produced during strong auroral episodes, acts as a radiative coolant, helping the upper atmosphere shed energy to space. This alters temperature and density profiles and can, through wave coupling, influence lower layers, such as the mesosphere and stratosphere, over timescales of days to weeks. These processes are part of top-down climate, forcing the influence of solar and geomagnetic variability on atmospheric dynamics. Auroras therefore provide not just a visual record of space weather, but a gateway to understanding how energy injected from above propagates downward into the climate system. Chapter 8. Civilizations that soar, light that speaks. If you've ever stood beneath an active aurora, it's easy to understand why ancient cultures believed the lights were alive. Long before spectrometers and satellites, people tried to explain auroras with the tools they had: myth, story, fear, respect. Vikings referred to the aurora as Bifrost, a glowing bridge between Earth and the realm of the gods. Sami traditions in northern Scandinavia regarded the aurora as sacred and avoided staring or whistling at it, out of respect for ancestral spirits. Some indigenous groups in Alaska described the aurora as spirits playing games in the sky. Although scientifically incorrect, these stories capture something accurate about the human response. Auroras feel sentient. They move in ways that trigger our instinct to assign intention and meaning. There are also historical reports of auroral sounds, faint crackling or rustling noises. Modern research suggests that under rare conditions, near-surface temperature inversions and electrostatic effects may indeed produce audible phenomena correlated with auroral activity. So while we now understand auroras in terms of plasma and magnetic fields, the sense that the sky is speaking has deep roots in human perception. Aurora has since entered literature, art, and collective memory as a symbol of contact between Earth and cosmos, a reminder that even before physics, the phenomenon shaped how people imagined their place in the universe. Science has decoded the mechanism, but not diminished the emotional impact. Chapter 9. Aurora, Earth's largest natural plasma laboratory. If you regard Aurora merely as a pretty light display, you miss its scientific depth. Behind each moving band of color is physics that mirrors some of the most energetic processes in the universe. Auroras let us study, at planetary scale, particle acceleration, magnetic reconnection, plasma waves, and current systems. The same principles govern solar flares, supernova remnants, jets from black holes, and cosmic ray acceleration. On Earth, we build complex devices, tokamaks, stellarators to confine plasma with magnetic fields and study it. In the polar sky, nature provides a full-scale, continuously operating counterpart. Auroral observations, combined with satellite measurements, offer direct evidence of how electrons are accelerated along field lines, real-time imaging of reconnection-driven substorms, data on wave-particle interactions that shape radiation belts. These insights feed back into both astrophysics and fusion research. Aurora is effectively a giant, open-air plasma experiment that we can observe again and again under different solar conditions without building it ourselves. Chapter 10, Aurora, as a dialogue between Earth and the Sun. In the world of plasma, charged particles, and magnetic fields, auroras are not just light. They are the visible form of an ongoing, structured exchange between our planet and its star. The story begins on the Sun. Eruptions accelerate particles, launch them into interplanetary space, and shape the interplanetary magnetic field. When those streams encounter Earth's magnetosphere, they distort it, feed energy into the magnetotail, and set up conditions for reconnection. Reconnection releases energy, accelerates electrons, and sends them down along magnetic field lines toward the poles. When those electrons strike Earth's upper atmosphere, the planet responds in light with emissions whose brightness, color, and structure all encode details of that interaction. Thus, brightness encodes energy input, color encodes particle energy and atmospheric composition, spatial patterns encode magnetic geometry, temporal changes encode magnetospheric dynamics. Auroras are, in this sense, a multi-channel visual record of Sun-Earth coupling. They remind us that Earth does not float isolated in space. It is embedded in the heliosphere, constantly influenced by solar variability. Life on Earth exists within this balance. Too little magnetic shielding, and the atmosphere would be stripped. Too violent a solar environment, and conditions would be hostile. Auroras are the boundary layer where we can see this balance in action, a thin, luminous interface between stellar output and planetary protection. Understanding auroras, scientifically, is part of understanding how habitable worlds survive in the radiation environment of their stars. And that is the deeper meaning behind the lights in the sky. They are not just decoration, they are diagnostics for the Sun, for Earth, and for the long-term stability of the environment that sustains us.